changes in two quantities. This is slope. Rate of change, slope, they mean the same thing. So here, when I say find the rate of change between each set of points, okay, we're going to look from here to here, and we see it went plus 2. From here to here, it went plus 6. Okay, from these 2 points, it was plus 2. And from these 2, it was plus 6. Now, even if you skipped 2, so let's say we went from here to here, that would be plus 12. Okay, to plus from 3 to 7 would be a plus 4. So when you look at that rate of change, the ratio, 6 over 2 is 3. 6 over 2 is 3. 12 over 4 is 3. The change in the y's, remember the bottom one, this one here, goes on top over the change in x's. So when you look at 6 over 2, 6 over 2, if you did, this would be 6 over 2. Even if you look from one point to another, they are always going to reduce to 3 in this particular table. Now, since that rate of change is constant, that it's always, at least when you reduce it, it reduces down to 3, these are called linear. So you can tell if a function is linear by looking at that rate of change. Again, excuse me. Find the change in the y and put it over the change in the x and see if that is constant. Now over here, now you have the tables in front of you. You're going to plot the points. Okay, so I have 1, 12. I'm going to probably count here by, let's see, maybe by 5s on this side. That's going to be my y's. This is going to be 0. And I'm going to, since it just goes 1, 2, 3, I'm going to count by 1s on the bottom. So I have 1 and 12. Okay. I have 3 and 18. So 5, 10, 15, 18 would be about here. I have 5, so 1, 2, 3, 4, 5. I'm going to go up to 24. 5, 10, 15, 20, 25. So it'll be about there. 7:30. And 9:36. Okay, so I'll plot the points. And you can see, even from the graph, I know it's a little crazy, but these all lie on the same line. So there's linear there. The line doesn't bend or curve, change direction. It's a straight line. Now you can show this constant rate of change on your graph as well in the slope. So you'll see here, this was a rise of 6 over a run of 2. And you'll see, I know it's a little hard to tell because I didn't use exact. So you'll see that all these triangles are the same. And even if you skipped a triangle and you went, I want to go from this point up to here, up to a different point, this again is where we had that rise of 12 to 4. And that's what's called a similar triangle. So your rate of change is going to show up in those right triangles. The 6 over 2. Okay, so all of these, the height by the length always reduces to 3. 6 over 2, 6 over 2, 6 over 2. So all of these are similar triangles. That is why it is linear. The rate of change is constant. So in the next one, does the table of values represent a linear or nonlinear function? Okay, I'll do one more with you, and then I'm going to ask you to pause and try the other ones with yourself, by yourself, and then come back and check in. So here I see a plus 1, a plus 2, a plus 3, and then a plus 1. Now, just because these are not the same does not mean that it's nonlinear. Remember, we're looking for that ratio of the changes. So here, I went down 6. So for this one, my ratio between these 2 points is -6 over 1. Okay, well, let's go from here to here. I went down 12. Okay, for those 2 points, I have -12. Okay, the y's went down 12 while the x's went up 2. And when that reduces, look at that. It's -6 over 1 again. So that's good for linear because the red and the blue are the same. And when we did red to blue, we looked at these numbers. In the green, I went down 18 from one point to the other. All right, so I'm going to compare the rise and run of these points. So I get -18 over 3, and guess what? That reduces to -6 over 1. Some of you might want to try the colors and see if that works. And then for the last point, I went down 6. That's right here. And over 1. So when you look at all of these, use this cool pen. Between the points, the rates of change always reduce to the same thing. So this is, let's see if I can change the font. This is a linear function. So this first table is a linear function. Notice how I kept doing the changes, and then I made the ratio of the change in the x, that slope. As long as they come out to all be the same thing, then it is linear. So now I'd like you to push pause, and I'd like you to try the rest on your own and then come back to check. All right, for this one, I went up 1. I went up 2. I went up 3. And this one, I went up 3. Up, let's see, 12. So I'm just even going to start here. I'm going to change, look at this to this. So in the first set, my rate of change is 3 to 1. In my second set of points, I have 12 over 2. That reduces to 6 over 1. Are these rates the same? No. So you don't even really have to go any farther. You can say right here, this is a nonlinear function. That's what you're looking for, nonlinear function. Okay, in this one, I don't like that pen for this. Now, in this one, it might look a little tricky. 5 to 2, we know 5 to 2 is not the same as 10 to 2. But this one has 5 to 2, so like 2 of them have it, but not all 3. Still nonlinear. All of these have to reduce to be the same thing. I understand that these do, but these do not. So it's still a function. We still have each input having only one output. So it is still a function. It's just non-linear, meaning it won't form a line. Okay, and in the last one, we added 2. And again, if you need to write all the fractions, do that. Do what you need to do to make this make sense. This went down 2, down 4. I know that one's a little hard to see. Down, let's see, 8. So look at this. This was constant, 2, 2, 2. But if these are the same, then these should be the same too, and they weren't. So again, this is a non-linear function. It is a function. Ooh, sorry about that. There's still, again, with that mapping diagram, it meets the needs of a function. It's just not graphing as a line. Now, remember this, y equals mx plus b. Whenever we graphed y equals mx plus b, what did it make? Did it make a curve? Did it make a circle? Did it make a V? And hopefully you're saying it makes a line. So anytime they ask if a function is linear, you're going to want to make sure it looks like this, y equals mx plus b. The important part is x cannot be raised to a power. That is your clue that this is not linear. For example, x, oh, wrong thing. Y equals x squared is a function, and we could make a table to show that, but it is not a linear function. Okay, again, whenever you have your y equals and I'll have an x and different numbers in, you need to make sure that that x is not raised to a power. That's your clue. In the last ones, are they linear? Why or why not? Are they increasing or decreasing? Why or why not? Not too bad, I don't think. You can see it, this is a line, but you can also show the constant rate. So this went up 3, back 1, okay? Up 3, back 1. So this is a linear function. Okay, as a constant rate of change. Let's shrink those words up a little bit. Okay, and when you look at it, you should be able to kind of tell if it's increasing or decreasing. Always start on the left side and move to the right. So if I'm going from left to right, you guys, a lot of you could see the negative slope here. Decreasing. Okay. Honestly, I'm not too picky there for you understanding the idea of increasing or decreasing. If you say it has a negative slope, if you said because it's going down, that lets me know that you have the idea. Now over here, this is not linear. And you can tell just because it's curved, but you can also tell by doing this. So from here to here, I went up 9, and I went over 3. From here to here, I went from 9 to 36. This is hard. Okay, I went from 9 to 36. So that is a change of 27. Okay, and I went from 3 to 6, so it changed 3. 9 over 3 is 3. 27 over 3 is 9. So see how the rate of change was different? So what you would say here, again, let me try to type this smaller. Non-linear function because the rate of change is not constant. Okay. And again, I think you can look at this too. There were no negatives here. I'm pointing at this, and you can't see me pointing to it. I didn't try and move backwards, so because of that, this is an